it is often said that you don't really learn anything until you start to teach it. And it so happens that the theme of autonomous racing was something that was interesting to me. I wanted to learn it. I wanted to learn how to actually drive with high velocity. So that's why I'm here. That gave me a pretext to prepare this presentation, to do additional research, and that is what I want to show you today. Let's start with a question: why do we even care about autonomous racing? There are multiple answers that you could give. There's this why not, basically. For me, it's just something very exciting. It's definitely a huge challenge to be able to control a vehicle with all the complexities that are involved in autonomous racing. And when I see solutions that are able to drive it, it's just basically like magic. For me, it's personally very inspiring. I hope that when you see what happens around the world, it will be also interesting to you. So this is more of a personal reason, but of course there are broader, you could say more important ones. If you think about racing drivers in general, what they do well is they are able to know the limits of their vehicles and know exactly how much torque they can apply, how much braking they apply, how can they turn, and so on. This obviously has direct applications in road scenarios. If you have a slicey road, for example, it's completely different from normal, let's say, highway driving. If a pedestrian comes before your vehicle, you also have to perform an emergency maneuver, and it's very important that you are able to utilize maximum performance of the car that you can get. It's this margin that might be very crucial to safety. Just imagine if every one of us who drives around the road would be a professional racing driver. I think the roads would be much safer, and this is something that can actually be done when autonomous cars have these capabilities. Before we start talking about some of the interesting designs that have been achieved, let's think about what actually is involved during racing. As it turns out, it's a very complex scenario. There are multiple forces to be considered. One of the, I would say, most important ones is the force between tires and the road. This is basically the only thing that you have direct control over. When you push the brake pedal or throttle or apply steering wheel, all that control is only really works through the contact with the ground. So this is the most crucial aspect of the vehicle to be able to control it. But of course there are many others. So on the bottom left you can see a very extreme case, that's for sure, but it's similar to what happens when cornering with high velocity. So what we see here is you have the centripetal force acting on the vehicle, which makes the center of gravity tilt towards one side, towards the outer edge of the curve. And because of that, you have different weights on each side of the vehicle, and thus you also have different frictions on each of the wheels. So when you drive like that, the behavior of the vehicle changes drastically. And last but not least, there are aerodynamic forces which come into play, especially with high velocities. We have two basic types. One is aerodynamic drag, which makes you slower when you drive. But the other force, which really comes together with it, so you can't choose one or the other, is the downforce. So the faster you get, at least when you consider design of a race car, you are pushed more to the ground, which in turn improves your traction. So this is maybe a bit counterintuitive, but the faster you get, the better you can stick to the road. Usually when you think about tires, you could think about a simple model where you just have a cylinder rolling on the ground and you have a wheel turned like that and the vehicle will go like that. As it turns out, it's not the case really, mainly because the tires are made of rubber, and rubber is a very elastic material. There are a lot of dynamics that come into play here. That's you really have to consider if you want to push the vehicle to its limits. So what we see on the left image is how the actual rolling direction of the tire deviates from the normal. You know what I'm trying to say, right? The line that goes along with the tire. I actually have a video too. So what we see here, we have something that imitates ground that the vehicle would be driving on, and it goes only in one direction, while the wheel is turning left and right. So the rolling direction doesn't change, but heading of the tire changes, and with it the threads of the wheel also deform, so that the tire is able to follow the desired direction. Because it's rubber and because it's elastic material, with this deformation also comes a force that acts in the opposite direction. So what we see here is an example diagram of how the lateral force that is being generated by tire slip relates to the slip angle of the tire. As a side note, maybe here, as I mentioned earlier, during driving, normal load on the wheel can change. And here we have 3 curves in 3 different colors. Each of the curves has different maximum forces. So these obviously relate to the different frictions between the road and the tire. Different load can be one reason for this, but also different road conditions, maybe slippery road. Also, if there's another force that is acting on the wheel, which I will talk about in a moment, it also can reduce the maximum lateral force that you can generate. So we know about lateral force dynamics. There's also another force that comes into play. This is slip ratio. So basically, how to understand it intuitively, it's the difference between how fast the wheel wants to go, because of how fast it rotates and how big is its radius, and how fast actually the vehicle goes. So this is a conflict between the friction and vehicle inertia. Obviously, if the tire starts rotating faster, then it wants to pull the vehicle forward. If the tire starts to rotate slower because of applied braking, then the vehicle will want to decelerate. All of this creates a very complex model of the vehicle, and it's very hard to understand everything of it, and to create a very accurate model. So sometimes it's more useful to use more abstracted views. So what we see here is an acceleration graph of a vehicle. In the vertical direction, you have lateral longitudinal Sorry, this is a very hard word. Longitudinal. Yes, longitudinal acceleration, which is acceleration along the vehicle, and lateral acceleration, which is acceleration in the other direction. What's most interesting here is the outer edge. This outer edge is the friction limit of how fast we actually can accelerate. So we have a few, let's say, pure cases, like pure braking, where we don't turn, we only apply braking on a straight segment of the road, so we can have maximum lateral acceleration. We can have pure cornering, where we drive with a constant velocity, and we can have maximum lateral acceleration, which relates to the centripetal force, which allows us to drive a curve and not fall out of the track. And we have transient states, where we brake a little, also turn a little. As you can see, this is not. This doesn't have benefit of either. So you can't. If you brake a little, you can't turn as much as you would be able to, and if you turn a little, you can't brake or accelerate. So this is an important trade-off that you have to take into account every time that you really want to drive at the edge. So after this bit of introduction about what really has to be considered when designing an autonomous racing control, let's start with some real examples. This is Shelley. It's an autonomous Audi created by a Stanford dynamic design lab. In the words of the creators, this is what the project is all about. It's an autonomous Audi TTS. It's designed to use all the available tire friction, enabling future autonomous vehicles to safely negotiate emergency situations. Researchers are working on to improve the car's performance by learning from professional race car drivers. And let me show you how this vehicle operates in practice. How do they do that? To answer that question, let's first think about what a driver does when he is negotiating a corner, which means just entering a corner. There are a few stages to that. Actually, maybe let's backtrack a little. When you race, usually this task is divided into two parts, which you do intuitively. First is creating a racing line. Racing line is the optimal path that you can go through so that you can have the minimal curvature of the track, and so you can drive with maximum speed. Once you have that path that you want to follow, your task is to drive that path as fast as possible without losing traction. On the example here, you have one generated racing line. As you can see, it is created so that the curvature is as small as possible. So it starts right on the apex of the curve and ends on the outer edges of the track. When it comes to actually driving the corner, starting from the letter A or even before, you approach the curve usually with a high velocity, and obviously this velocity is too much to be able to stick on the curve. So to be able to enter the track, you hit braking earlier. which on this right diagram, which is similar to what we saw earlier regarding acceleration limits, it relates to maximum braking. So you drive on a straight, you don't have any cornering, you brake as much as possible. Then you have curve entrance, which is the segment between A and B. And there is where the curvature starts to rise. So you go from going totally straight to turning, and the amount of turning increases until you reach the apex. So this, on the diagram, you go from maximum braking to slowly releasing the braking pedal, turning more and more and more, until finally you hit the segment of the curve where you drive with a constant radius or constant curvature. You do only cornering, and this is important because if you wouldn't drive with a constant speed on the apex, so if you were below or above this point, obviously you have less available lateral force, which means that you have less centripetal force that you can overcome, and well, you can't drive as fast as you can. So in order to be able to drive the curve with maximum speed, you have to be able to drive the apex with constant velocity. After leaving it, the situation is turned. You slowly start accelerating and straighten the driving wheel until you reach the corner exit, where you can just accelerate until you hit the maximum speed. Three main things to remember. First is that you start braking before you enter the corner, otherwise you might not be able to decelerate fast enough to be able to reach the desired speed. Second, when you actually enter the corner and start turning, you have to carefully balance how much braking and how much turning you apply. And the third thing is what we just talked about a moment ago. When you are at the apex, or more generally at the constant curvature segment, you don't want any lateral acceleration. So, following that general, let's say, algorithm of how a race car driver approaches a curve, the controller for all the TTS was designed. It was combined of two main parts. First is path generation, so this is generating of the actual racing line that we want to follow. And second, knowing this racing line and knowing vehicle limits, you generate speed and velocity profiles that allow you to enter the curve as fast as possible, and also calculate how do you actually want to turn the steering wheel so that you follow the path as well as possible. And finally, there's one more step to it, which is just to add stability and compensate for some modeling errors for things that we might not consider. As you know, driving is a combination of a lot of forces that come into play, and in practice it's impossible to model everything so that you have perfect predictions. That's why it's important to also have a feedback loop that allows you to make adjustments to any errors that might arise in the way. So, a bit of math, but really a bit. This is how the path is defined. This curve has some name, but I forgot it. It has something to do with Euler, that I'm sure of. But what is important here that we partition the racing line into segments. We have a segment with constant curvature equals 0 before corner entrance. We have a segment with linear curvature, as you can see here. And this curvature increases linearly until we hit the constant radius segment. And finally, when we leave the corner, we slowly, the curvature slowly falls down back to zero, where you have a straight segment of the path. From this slide, what's important to remember is the formula for the curvature, which is 2c²s, where c is just some coefficient that tells you about the shape of the curve. So when we generate the racing line, this c parameter is something that we have to decide on, and c is just a distance along the track. So s would start here with 0 and increase in this direction. A word about friction limits. So we used, they used a simplified acceleration diagram, which is just a circle, which is depicted in this first equation. So the maximum acceleration that the vehicle can have is just a square of it is just a sum of squares of lateral and longitudinal acceleration. Then we can calculate what the lateral acceleration really is. And if you remember from physics, it's just velocity squared divided by radius. But radius we already know because, well, the inverse of radius, so curvature, is 2c²s. When we place it into the first equation, we finally get the formula for the lateral acceleration that we actually can have at any point on the curve, which maybe I'll not say out loud, but yeah, you see how it looks. Now for the speed profile. How fast can we actually go when we are approaching a curve? First, I think the simplest case, pure cornering. So this is the situation where you actually, when you have already entered the curve, when you are driving in the middle, and this is the place where we want to have the constant velocity. You know the curvature, and you know radius of the curve, which is r. You know your maximum acceleration, and you also know that the lateral acceleration you want to be 0. So from that you can easily have the desired velocity, which is the maximum velocity that you will be able to drive without losing traction on this curve. More fun begins when you want to decide how fast do you want to brake or accelerate on the transient segment. First, let's notice that lateral acceleration is just a derivative of velocity, also lateral, over time. And this in turn, when doing some chain rule magic, gives you this form. And ds over dt is obviously just the lateral velocity. So moving everything around, you can have a differential equation for the rate of change of speed. And this you can just solve numerically, which gives you speed from apex of the corner up to the entrance or up to the exit of the curve. And last bit, how far before the corner you have to start braking. Because we already established that you want to do it early enough so that you are able to decelerate to a desired velocity. On the other hand, you don't want to do it too early, because if you do that, you will lose a lot of velocity that you would be able to utilize otherwise and lose precious time. This is really just one of the main dilemmas that race drivers have to face. So a lot of racing practice is just learning where to brake, where to accelerate, knowing the vehicle limits and how it relates to the road. So the distance, how far you have to brake before entering the curve, can be given by this equation, where ux is a velocity that you're driving before entering the curve, and UX entry is the velocity that is calculated from the equation above. So this is the velocity that you want to have on the entrance of the curve. Maybe I'll not go into that much detail when it comes to the steering angle, but let's just say that knowing geometry of the vehicle, knowing the dynamic equations for steady state, and also equations for the forces. And maybe a side note here. At the beginning of the presentation, I was talking about slip angle, which is here denoted as alpha. You saw the curve that firstly rises somehow linearly, and then when it reaches maximum value, which is due to the friction, it starts to flatten. Here we approximate just by this linear segment. So this is a good approximation as long as we are not near limits of the tire, which we of course want to approach, but this will be solved by a feedback controller later. This is better shown here on the slide. So the blue line is the relationship between the lateral acceleration that we want to have and the feed-forward steering angle that have been deduced from that. And on green and red, you can see the limits, the actual limits of the vehicle. So with the biggest lateral accelerations, you can actually see that you go below the oversteer limit. So this is something that has to be taken care if we want to have a stable vehicle. So having that, we just to recap, we have velocity profile. When we differentiate that, we can also have lateral accelerations, so we know how fast we want to go and how fast we want to accelerate. We also know how much we want to turn the steering wheel. Now we can go to the feedback part. So first part of the feedback is deviation of the track. In a non-ideal world, so in any world, basically, you won't be able to follow the path exactly. You will always be a bit off, which in here is denoted by the error, the lateral error E. We also use some look ahead, so we don't only look at how far is the center of gravity of the vehicle. We actually look a bit forward to a point called XLA. And this deviation from the path at this point in front of the vehicle is used as a gain to a control, to a feedback control. So you generate a control input that is proportional to how far are you, how far away are you from the goal. Second part of feedback is related with yaw damping. This is related to yaw oscillations. Have any of you worked with proportional controllers, maybe? Okay, so what we saw before was a proportional controller, and what it does, it creates steering based on how far we are from the goal. But it means that if we start far away from the goal, the combined steering might eventually become so large that we go not really in parallel to the road, but cross it at a very high angle, which means that instead of following the curve as you would want to, we overshoot it in one direction, then the feedback starts working in another direction, and you basically go like that. This is undesirable. Well, there's a main reason why it's not desirable. It can show in different forms. Just remember that when you start turning, you have less available friction. So one less extreme case is that when you oscillate, you can't accelerate, or you can't accelerate, or you can't decelerate as fast as you could. But the more extreme scenario is that you actually start having so much oscillations that you eventually lose grip. So this is another thing that I would like to show you how it happened in practice. So this is a video of Robocar. This is autonomous car that's actually at the moment holds a Guinness record for the fastest autonomous car. I won't show you the entire video. I just want to show you a small bit of it about the problems that you can have when you really want to push the vehicle to its limits. So this will be from the early tests in 2018. So just driving straight, but notice in a moment you will change view. There are a little oscillations, not really much, but a moment later you lose grip entirely and it's done, basically. So I think that you saw that the oscillations weren't really that big, but even that was enough for the car to lose control. That's why it's important to actually be able to control your oscillations of the vehicle. So how do you do that? You look at how fast the heading of the car changes, and you add feedback proportional to that. So it's called a derivative controller, which means that the value of the control is proportional to how fast the value changes. Having these three values, the feed-forward steering angle, which we developed just from equations, the control feedback, which is related to how far we are from the track, and the damping feedback, which is related to reducing oscillations, gives us the combined steering angle that we use to actually control the vehicle and turn the steering wheel. So this is one part of the inputs. The other one is lateral, so how fast we actually want to accelerate. These curves might be somewhat familiar if you try to remember. This is actually half of the curve that I've shown on the previous slide. It's also inverted because it's only talking about absolute values, so it doesn't care if it's inverted or not. The curve on the top shows available lateral force relative to the slip that appears on the wheel. And below we have a similar curve for the longitudinal slip, which is related to the tire slip ratio. In practice, it is useful to think about these two as relating in something similar to the acceleration diagram that you saw before, which is shown here. So how you can think about it is that if the tire causes the vehicle to accelerate a lot, it can't at the same time cause it to turn a lot. So this is a similar case to what we had with the general view. Just this time we're looking at individual tires. And at the bottom we have, just for utility, a simple normalization so that we have a unit circle. So the alpha with a dash above will be alpha divided by the maximum value, and similar with kappa. So based on that knowledge, a slip circle controller can be developed. So it looks at which point are we in the circle, or usually how far are we away from the circle, and based on that it sees how much available longitudinal force it has, which can be increased or decreased depending on what the actual situation is. So this part of the controller just deals with the friction limits and how not to exceed it, but on the other hand, how to be as close as possible. Also, we have a feedback that is related to the speed that we wanted to have. it might happen that we are on the path where we want it to be, but our speed is different. So what we can do is just add a little bit of throttle, or if it's an opposite situation, a little bit of braking, to compensate and be as close to the desired state as possible. So these three components of force, which is feed-forward force that has been generated from acceleration, feedback, and speed, which we have seen just before, and only last bit, which is related to aerodynamic drag. So this is basically a compensation. You apply some force for the vehicle to go forward, but you also have some force dragging you in the opposite direction, which is usually the air. You just see how much of force that is and apply additional force to go faster. That's the basic concept. Okay, so we went through the math. Now, how does it actually result in practice? So this is an example of actual cornering on a testing track. We start at the middle of the circle. So this is a place where we have approximately zero acceleration, which means we are driving straight and with a constant velocity. And then at some point, we are approaching a curve. When we are approaching a curve, before the curve, still driving straight, we hit the brakes. So we go to maximum negative longitudinal acceleration. Then at some point, we enter the curve. And then it's important to remember balance the two accelerations. So you release the braking pedal and simultaneously start turning more and more and more and more. Then you hit the place where you drive just on the curve. So you have no acceleration, you have no deceleration, you just drive. And then the last part, exit of the curve, where you're able to slowly accelerate and simultaneously start cornering slower. Right. So that was it when it comes to math. It was maybe an experiment from my side, how much math I can push these presentations. I think that was a bit too much, if you agree with me. So now we will just focus of what cool can be done with different algorithms. So this is from the same team that created the vehicle that you have seen before. But the difference is that before they wanted to drive below the friction limits as fast as possible, and here they want to drive above the friction limits. So basically they want to drift. And that's what they do.
Full autonomous mode in 3, 2, 1, go.
I just want to wait for the part of the video when it really shows how good it can follow the curve. Yeah, so you can see a quite long segment here, and it really hits how it wants to hit. Okay, I think that's it, because it will be just doing the same thing over and over again, but you get the idea. It's really precise. I can't do that. I don't know about you. But yeah, it looks pretty cool. Yeah, what they say about themselves, something similar to what we saw before. And last bit of the presentation, where I want to talk about a bit different methods about driving, because what we had before, we basically analyzed the curve that we want to follow, and then based on that we calculated the desired speed or desired steering angle. Here the approach is a little different. It's called model predictive control, and this time really, without going into any maths of it, you have some initial vehicle state that you are driving, and from this vehicle state you ask, how do I want to drive, what commands do I want to apply, so that I can drive the best it's possible. So during the algorithm, a lot of times different command sequences are evaluated, and based on that command sequences you see, okay, if I do that, if I brake now for 2 seconds and then release and then turn, where will I be? And how does that relate to actually the goal that I wanted to follow? One of the coolest examples of that is definitely model predictive contouring control, which was developed at the University of Zurich. I think an interesting bit about it is, as you can see, it's nowhere near close to an actual vehicle. This is 1 to the 43, yeah, 1 to the 43rd scale. So it's something like this. And even having cars like this, which are basically just toys, you can have valuable research that is also used worldwide. So you don't need large budgets, you just need creative ideas. And as you'll see in a moment, they can create. This is real time. If you thought that was interesting, look now. We have actual 2 vehicles that are driving simultaneously. Each of them is being controlled independently. So you have a battle of algorithms, 2 racing cars that are driving against each other. And yeah, you see some overtaking, even in slow motion. This is an overview of how the actual setup looks like. So these are really small colors. You can't fit any compute power on there. These are controlled by remotely by Bluetooth. So what they did, they have this racing track that you saw. Above it, there's an infrared camera, and on each of the vehicle there is a marker that reacts to that infrared light. So having that camera, you just look at the markers and know, okay, this vehicle is here, this vehicle is here, this vehicle is here. This is all done by the central computer, seen here at the top. Having information about positions of each of the vehicles, it then distributes this information to controllers that are responsible for each of the cars. So, yeah, that's the general flow of the algorithm. What's interesting about model predictive contouring control is that you don't care about racing line before you make it running. So the reference path here is shown where everything here is black, but the one in the middle, this is the reference path that you use. As you can see, it's not optimized in any way. So you have information about your position, you have information about this path that you want to follow. So the goal really is go as fast along this path as possible while staying within the limits that are depicted by the green dots. So this is more or less the goal that you have. Go as far as you can without hitting the walls. And based on that, it's able to actually generate really good trajectories. As you can see, when entering a chicane, which is just a set of 2 turns in opposite directions, it knows to drive straight into them, so it doesn't have to lose velocity to do 1 or the second turn. And also here is shown how actually the obstacle avoidance is done. So when we had the track boundaries that we saw before in green, here these boundaries are modified based on where the obstacles are in the path. So the left border is still where it was, but because on the right there are obstacles, now the road boundary approaches closer and closer to the corridor, until at the end you really have only this very narrow part of the path that you can go through. This algorithm was used by a Formula student team, AMZ Driverless. It's from the same university also. So Formula Student is a competition for teams that revolves around creating their own racing cars according to very strict specifications. And one of the categories for Formula Student is a driverless competition. I'm not sure when it started. It's pretty young, but nevertheless, the team that you see here, AMZ Driverless, I know that it's won at least until 2017. I don't know about before because I didn't even know if the competition existed, but they're really good at what they do, and they are far above their competitors. Maybe this last year, actually, there was one team that came pretty close from Germany, but when you summed up the points, they had 800 something, the second team had 800 something points, and the third team had 400 points. So you can see the gap is pretty wide. I don't really know how the points are calculated. I mean, I try to understand it, but it's not really that important. What's more important here is the distance with points between the cars. So as we established, they use model predictive contouring control, but they also use a bit of a, well, maybe not a secret sauce because it's made public, but a bit of a special sauce. They utilize Bayesian techniques to estimate how different is the model that they have from actual predictions. So if you don't know what I'm talking about, just to repeat and maybe make it more clear, model predictive control relies on making predictions based on a vehicle model. So you have a vehicle model, you have your commands, and you see, okay, if I apply this command to the model, where will it be in 2 seconds? This is the basic idea. And as you also know, it's very difficult to model precisely a vehicle. So if you do it analytically, there will be always errors. So what they do, they run an online algorithm that looks at these errors, looks, okay, this is the prediction where we thought we were, this is the prediction, this is the state where we actually are, this is the difference. And to compensate that, we would have to add this value to the prediction. So let's say we should be really predicting that we are a bit more to the right that we thought we were. Here the road boundaries are defined by the currents blue on the left and yellow on the right. There's an additional step with computer vision that you actually have to find these cones and you have to create a map of the track. But when you forget about that, when you assume that you have that done, this is actually the same thing that we saw before with the smaller cars. So you have a corridor here in the red, you have predictions in green, and you have the actual curve that you are following in white. And if you look at the left, you see how the lap time gradually improves from 20 seconds to 18 seconds in the 8th lap. So the difference is that at the beginning they were using the analytical model that they just created based on the vehicle, and afterwards they were using the model that was trained based on the actual data that they gathered from driving. So it just drives and drives and drives, and with each lap it becomes better. And last one that I want to show you, I would say that this is an opposite spectrum to MPCC, because with MPCC we started with model predictive control with a model that we knew before starting, which we calculated just knowing all the parameters of the car. The second, which is called GP MPC from Gaussian process MPC, is somewhat in the middle, because it uses a reference model, but then improves it with time. MPPI, on the other hand, it doesn't have an original model. It is based purely on reinforcement learning. So you drive it on the track, it looks at how the car behaves, and based on that, it makes prediction how would it behave in different scenarios. This is enabled by a different technique they're using for MPC. And so the two controllers that you have seen earlier, the general working principle of it is that you start with some command sequence, you evaluate it, you compute the derivatives, and you see, okay, so which direction should I go in order to be able to improve the result a little. And then you do it again, and again, and again, and again, and again, until finally you reach something that is close to optimal. The problem with that is, for example, you can hit local minima. So if you have a very complex model or very complex cost function is just a measure of how good a trajectory is, you might have problems with being able to optimize that. So these guys went with a different approach. They said, okay, let's not just do one trajectory and try to improve it. Let's do a few thousand at once, and let's see which one is the best. So this is a bit of a brute force approach, but it's made possible because of the recent advances in GPUs and in parallel processing in general. So they basically throw a lot of computing power at the problem and see what comes out. And they also, based on that, can have very interesting results.
This video presents the MPPI algorithm and experimental results on the AutoRally platform at the Georgia Tech Autonomous Racing Facility. In all clips, the robot operates fully autonomously, using only onboard computation at speeds approaching 20 miles an hour. MPPI, which stands for Model Predictive Path Integral Control, is a stochastic optimal control method that relies on forward sampling trajectories. These trajectories allow the algorithm to evaluate many possible control sequences. A simple approach would be to then select and execute the most desirable control sequence. However, one sample trajectory is very jerky. Instead, computing a weighted average of the sequences according to their desirability gives a smooth, low-cost trajectory. Unlike most traditional optimal control methods, there's no need to backpropagate information during the optimization. Also, sampling trajectories is a naturally parallel task which can run in real time on a GPU. The dynamics model used for forward sampling is a linear function of 25 features that a nominal trajectory is shown in green, and the sample trajectories are shown.
So these are the 2,560 trajectories that are...
One time step of controls are applied, then optimization is repeated. This process runs at 60 Hz on board the robot.
Anyway, yeah.
The trajectories are shown on the left as they're sampled in real time.
Yeah, so in white there are the multiple trajectories that are generated. Each of these is evaluated, and the best one, well, not the best one, as he said, average of a few best ones is generated as the green one, and the vehicle is able to drive on a road which is not very easy to drive for an automatic controller, because it can change really quickly how much grip you have. And that's also it when it comes to the presentation. I hope that maybe some of the solutions shown here interested you a bit. If you want to maybe work on your own cars, I know that some people, including one that will be presenting just after me, want to design algorithms based on smaller scale cars. These are the papers that you can use. This is actually just going from the beginning to the end, what I talked about in the presentation. So feel free to take a photo and refer to it later if you like.
Thank you.